my presentation on modeling vegetation dynamics in wetlands using machine learning and temperature data, a case study in Louisiana's Plaquemines Parish. Oh, okay. So wetlands are really important to our ecosystem because they have the ability to filter water by detoxifying chemicals and filtering sediment out. They provide habitats to many biodiverse species, and they can alleviate floods. And most importantly, they are carbon sinks, which means that they can store more carbon in the atmosphere, in their ecosystem than they release into the atmosphere. And this is especially important to mitigating global warming. So an issue, though, is that they are, however, rapidly disappearing. For example, in Louisiana, which hosts 40% of the country's wetlands, 1/4 of the wetlands have been lost since the 1930s. So in Louisiana in particular, a $50 billion plan was created in order to restore wetlands. And one of the main objectives of wetland restoration is to, one of the main objectives of wetland restoration is to restore species diversity, which is reliant on vegetation. And as a result, it would be beneficial to have an easy to access way to monitor vegetation in wetlands. So patterns of change in vegetation can also be referred to as vegetation dynamics. By accurately predicting vegetation and dynamics in wetlands, we can restore efforts and inform environment. We can guide restoration efforts and inform environmental law. So to predict vegetation dynamics, satellite imagery can be used. The Normalized Difference Vegetation Index, also known as NDVI, is a formula that can be used to assign a numerical value to the presence of vegetation, and NDVI is essentially a measure of greenness, which indicates the presence of photosynthetic pigments. The formula can be seen here, and in this study, NDVI will be used as a measure of vegetation, and I may occasionally use the words NDVI and vegetation interchangeably. So in order to analyze the trends in NDVI or vegetation, machine learning can be used. Machine learning is a type of artificial intelligence, and using machine learning will help automate the process of monitoring wetlands so it can be done on a large scale. And this type of prediction classifies as a time series machine learning problem, and time series essentially refers to data where time is the independent variable. And in this case, we are predicting vegetation over time, and there are a variety of machine learning models that can be used for time series prediction. The seasonal autoregressive integrated moving average model, also known as SARIMA, is a commonly used model for time series forecasting, and neural network models also provide another alternative. In particular, a specific type of neural network known as the long short-term memory model, or LST model, is a good candidate for this type of data, and LST models have an internal memory that can be taken into account while making predictions for data.
Anusha, I'm sorry, your slides are blocked by your notes. I don't think you.
Oh, I'm so sorry.
It's okay. I was trying to find a good place to let you know. Because your slides aren't full screen, we see your desktop still.
Okay. Here, I'll go like this. So, previous work in the field includes, so previously machine learning has been used to predict vegetation dynamics in forests. However, it hasn't been focused as much in wetlands. And so wetlands are different from forests because of the hydrological variability. And so as a result, it's very important to be able to model vegetation dynamics in wetlands because it's different. And so this study also aims to assess using supplemental climate data into using supplemental temperature data as a supplement to the LST model. And so 3 models will be made. The first one will be the SARIMA model, the second one will be the NDVI only LST model, and the last one will be the multivariate LST model, which will include both NDVI and temperature data. So for my review of literature, these first 2 articles have to do with the location I selected. The first one is called Carbon Storage and Fluxes Within Freshwater Wetlands, a Critical Review. And so this article I mainly used to learn more about the significance of wetlands. The second article is about the significance, particularly of the Plaquemines Parish, and why it's important to look into that place, which is the area I selected for my study. This third article is a review of wetland remote sensing, and it's basically different ways that satellite imagery has been used to kind of detect information about wetlands, and it talks a lot about NDVI and why that can be used as a measure of vegetation. These next 2 articles I used particularly for my methods and materials. So the first one I used for creating my SARIMA model. The second one I used for creating my my LSTM model. And then this last article, it has to do with a different sort of problem. It's about predicting a certain type of fever. Um, However, it does compare like a specific type of Surima model and an LSTM model. And so I used it to kind of figure out why my discussion or my results ended up the way that they did. So my problem statement is, can machine learning be used to accurately predict vegetation dynamics in wetlands, and what type of model will be the most accurate? So machine learning can be used, my hypothesis is that machine learning can be used to accurately predict vegetation dynamics in wetlands, and the multivariable LSTM will be the most accurate because of its ability to have a sort of memory, and because the temperature data will aid it as well. So for my study area, I chose the Louisiana Plaquemines Parish, specifically because wetlands there are in a lot of danger, and also additionally because oil is a major industry in this area, which has also put the wetlands in danger as well. And so what I did is I used Google Earth Engine, and which is a publicly available data set. And so I took satellite images for the course of 21 years and calculated the average temperature values and monthly NDVI values for 10 locations, which resulted in 252 data points total and 252 points per location. And so here's an image showing the different locations. So I created 3 machine learning models once again. So the first is the Surima time series model. This model is the baseline model, and it's hypothesized to be the least accurate. The second one is the LST model, which is constructed with only NDVI data. And the third one is the multivariate LST model. And this one was made with temperature and NDVI data, and it's hypothesized to be the most accurate. In order to evaluate my models, I used root mean squared error. And so what this does is it measures the difference between the actual values and predicted values, and lower root mean squared error values correspond to more accurate models. And so it's abbreviated as RMSE on the slides. So first I constructed the Surima model. This stands for Seasonal Autoregressive Integrated Moving Average, and it's actually a variation of the ARIMA model, which is just the same thing without the seasonal. And what it is it's modified for the seasonality. So normal NDVI, normal ARIMA models can't account for seasonality, which is when there are trends in data such as vegetation, which goes down during the winter times and up during like the summer times. And so this one can account for that. And so the parameters for this are P, D, and Q, which corresponds to autoregressive, D corresponds to integrated, Q corresponds to moving average, and then the uppercase versions of those letters are just the seasonal counterparts of it. And then S corresponds to the length of the season. So for this study, I set S to 12 to represent one full year. And I set so for differencing, or D, that stands for integrated as well. What that is if data is not stationary, the Surima model can't handle it. So we need to make data stationary. And so how we do that is we use differencing. And what differencing is essentially taking the current point and subtracting the value of the last point from it. And the amount of times differencing needs to be done to make data stationary, meaning it doesn't go up or down over time, is the value of D in the model. And that's what we plug in. And then for the parameters P, that stands for the autoregressive or AR part of the Surima model. And so what autoregression is it essentially assumes that the future is some repetition of the past with an amount of lag. And so the P value is the window of that lag. And then what moving average is it's essentially the same thing as P, but with the errors that the model makes with forecasting. And so in order to calculate these values, I used Alkaline's information criterion. And so I set the values of P's and the P's and Q's from the range 0 to 3, which resulted in 81 possible combinations. And then the combination with the lowest AIC corresponds to the combination that would have the most accurate model. So I plugged those values into the Surima model. So the next model I made was the long short-term memory model. And so this model is a type of neural network. And just to explain the basic structure of a neural network, what that does is there are different nodes or neurons. And so it sort of mimics the structure of a brain. And each of these neurons have a certain amount of weight that shows its significance on the final output or prediction. And so regular neural networks can't keep track of these weights. They kind of forget them as they go on, but long short-term memory models, they can keep track of these weights as they go on, and that's what the memory part of the long short-term memory is. And so the way that they do this is that their neurons are structured as a memory cell like this. And they have a forget gate, an input gate, and an output gate. So the forget gate demonstrated here, what it does is it removes information that is no longer important. The input gate decides what new information is relevant. And the output gate decides what information should be passed on to the next cell. And so for the LSTM model, the data was split into test versus train. And so the testing data is essentially data that is like data that the model hasn't seen before, and it predicts what the results will be. And so it offers a more accurate evaluation of the model's accuracy. And so I've circled the most important values for my results here. So as a reminder, root mean squared error was used, and lower root mean squared values correspond to a more accurate model. And so the Serena model had the lowest, and then it was the NDVI LCM one, and then the last one was the multivariable, so that was the least accurate. So as a reminder, my hypothesis was that machine learning can be used to accurately predict vegetation dynamics and wetlands, and the multivariable LST model will be the most accurate, and this was only partially supported. I learned that machine learning can be used to accurately predict vegetation dynamics. However, the multivariable LST model performed the worst, and the UREMA was actually the most accurate, or SARIMA. And so what I found was that the SARIMA model had the most consistent root mean squared error, and the NDVI only LSTM model was more accurate for certain locations, but it depended largely on the location. And what this indicates is that the model was too complex for the small data set that was used, and it actually overfit in certain locations, which means that it was too attuned to the data it was trained on, and it couldn't deal with the new data that it was given. And then the multivariable LSTM, it performed the worst. And I think it was because this was confused by the conflicting trends between temperature and NDVI. When analyzed, temperature and NDVI had a positive correlation coefficient, which indicates that as temperature increased, NDVI should have as well. But NDVI, like, it depended largely on the location. And so as you can see for location one, temperature had a slightly positive increase, but NDVI was very clearly downwards, and only including temperature data may have been a simplification, too much of a simplification of the factors affecting wetland growth and decay.
Time.
And so, okay. Thank you so much for listening.
Thank